Good morning. This is part three of a series of lectures or webinars on LC-MS unknown identifications using MSMS libraries. Part three is more detailed discussion of MSMS hybrid search. I talked about it a little bit in part two, but this type of search is much different than the other two that I discussed. So I wanted to break it out into a separate one. And it's also the one I'm most excited about. It's a very powerful way to extend the dynamic range of your database for searches. Like all of the ones that I've given so far, there's a detailed description on my website about how to reproduce the parameters for doing this. There's a lot of settings that you have to use to properly set it up, and they're discussed in the handout, plus a lot of other things in more detail for trying to explain what the hybrid search is and how it works. So take a look at that. And this is, again, like I said, part of an 8-part series that talks about the utilization of the NIST search for identifying unknowns using MSMS libraries. I had done another one about electron ionization MS searches of the NIST database, but I felt like a lot of people weren't using the MSMS like they should. I think there's a very good potential for using the MSMS libraries, especially the new ones in the NIST 2020 edition, to do a very good job of identifying unknowns. So it could be very helpful. So I wanted to share a discussion of all the different things. And it's somewhat different than the EIN, and it's a little bit harder than the EI to get results, but I think it's still very much worthwhile. So let's talk a little bit about the program description. The hybrid search generates a hybrid score matching fragments and neutral losses. So it calculates two different scores and then merges them together to get the hybrid score. So it does a traditional matching type fragment spectrum like you would expect, but then it looks at the neutral loss spectrum and combines that score with the matching fragments to get this hybrid score. So it greatly extends the scope of the library by including nearest neighbor. So you really don't have to acquire more spectra in your library. Things that differ by groups start to show up in your search results and give you an idea of what your unknown might be without actually increasing the size of the library. But of course, the success requires the presence of similar compounds in the library, and the mass difference must be confined to a single region of the molecule and no significant alteration of the fragmentation behavior. So all that being said, it still works very well. There are some limitations, but those limitations are met in many cases. So you get a lot of things that you wouldn't expect to get from the search results. And one of the key things in this is the delta mass, is the difference between the query and the library compound, and reflects the modification of the molecule. And we'll talk about that. I have a table of ones that I've put together in some of my work. I've personally used the hybrid search in EI mode for a couple of years now, and I'm routinely amazed by the types of similar compounds with high match factors that come up. And it very frequently gives useful results not noted in the simple standard fragment search comparison. It's very useful in finding similar model compounds, support for fragmentation mechanisms, and I believe identification of unknowns. And it should be very useful in MSMS searches for similar reasons. So let's go to the search program now and do a hybrid search. The first thing that we talked about before, about using any of this software, you need to set up the settings. And this is the library search options. If you hover over it for a second, it'll say what it is. And if you open that up, you have to set up all of these tabs to get the proper search results. And I put this in this handout. It was also in the handout for the previous session, but I also duplicated it again if you look at the details for this particular webinar. So take a look at it, make sure it's set up. And after you get it set up, the thing that you want to do is say save configuration. And I saved this one called Hybrid Demo YouTube Example. So after you save the settings once, they're there, and you don't have to go and bring them back in every time you get ready to use the hybrid search. So I set up the different searches with different configurations that can be easily recalled. That's a very powerful way that the NIST search works, and that you can save these settings. So as we said before, these are always our unknowns that we're working on here. This is the results. This is our unknown spectrum and some details that might come in with it from the manufacturer's software when you're data processing. We have a display, a head to tail, that we'll talk about in more detail, and it's much different in this head to tail, and I won't discuss it much in the active software demonstration. But when I go back into the PDF of the details, I'll show you a little bit more about that. And of course, here are the ones on the bottom that show you what your search results are. So let's do a search. You can hit double left mouse button, click on this, or you can hit go. I just want to double click on it to get the results. It searched the library and gave us about 38 spectra here. Let's do that again. It was about 38 spectra. If you look up the top, it tells you that it did a MSMS hybrid pre-search and came up with 38 possibilities. And if you go down and look at them, you just click on the first one, and then you can use the keys on your keyboard to look through it. You can see there's 3 right off the top that are really pretty much the same thing. The thing that's important about MSMS libraries to get good searches, you have to have them at many different energy levels to make sure it matches your energy level on your particular instrument and configuration. But here we found 3, and the dot product is the best way to compare. You can see I got a 954 for it. The score doesn't mean as much, but when they're close, it gives you an idea that there probably is a good, reasonable match. And so this is a really good match, 954 by the hybrid search. You can see it comes down to another entry further down that's somewhat related if you're looking through the results. But what I do a lot of times after I do the search, you can go up and you can filter it by, if you hover over this, it says best matching only. And that's by using the CAS number to eliminate duplicates. And so we're going to watch this number. Now it's 38. This can be done after the search, so you can go back and forth. But if you click it on, now you have 15. And now when you click through the results at the bottom, you can see that it jumps down and skips all the duplicates. So it's kind of handy to do that, but I usually don't have it on initially, but just toggle it on as I look at the results to make it a little bit more efficient. So the key thing that we want to talk about here is, let's go back and put it on the smaller results, is this delta mass value, 33.9610. If you look up the accurate mass for that, and we'll talk about that in our delta table example, I'll go back into the details in the presentation as opposed to being in the software. 33.96 indicates that there's a difference in a chlorine. 34 is about the nominal, but 33.9610 is dead on for the presence of a chlorine compared to this molecule. So if you take this molecule down here, it's telling you that the molecule is 33.9610 or a chlorine higher than this. So it's got looks like it's probably got a chlorine on the ring as compared to this species here. The other nice thing about it is you can resort any column that you want to. So dot product is the one that we normally have that shows the hybrid fit. But I told you when it does the comparison of the molecule, it looks at the lower end or the spectrum as with respect to a fragmentation. You can see it didn't match real well here, 117. So it's really matching more on the neutral loss. I'll show you in a second. But if you want to resort by this, that's really just saying, if I had done a similarity search just by the fragments in the spectrum, which ones would have matched this? What kind of compounds? And you can see it's much different now. So if I come here, I'm going to select the first one and start stepping through them. So you can see, I want you to watch this as I step through them in the bottom here. And I'm going to step through a couple of them. You can see that what it's telling me is that everything that matches just the pattern, but not the neutral loss or the hybrid, has 2 chlorines. So that kind of confirms that we thought that the molecule had 2 more chlorines, and the chlorines are on this aromatic ring. They're not somewhere else within the molecule, like on the thiophene part of the ring. So that just gives us more information. So I always resort by the ODOT product, which is the original fragmentation type spectrum scored separately before it did the hybrid score. And it'll tell you something usually about the substructure. As you step through them, I think almost all of them have a dichloro except that one's the last one, and it's fallen off, and the ODOT product is down to 117 now. So all the high fits for that reverse indicate that the chlorine's on the ring. Let's go back to the ODOT product again. If you look over at the spectrum, if you tried to fit this pattern versus this pattern, you would say it doesn't fit at all. And you'd say, I don't really understand why it's finding things. So sometimes it's useful just to go over and right click on the center display and say neutral loss display, and then compare the spectra. If you do a neutral loss display, what it does is it takes the molecular ion or the precursor ion and subtracts the different masses from it to get the neutral loss spectrum. So it shows off almost 0 at the molecular ion region. It loses 100, loses 76, 136. So you can see visually now that yes, these spectra were very similar. And what the hybrid search is telling you is, yeah, the fragments tell you something about the hybrid score, but in this case, the neutral loss spectrum will give you a very good indication. Yes, the spectra are very similar, very similar. So I was looking through my list here to make sure I didn't leave out anything. I think that's all that I wanted to tell you in the actual software presentation. We've shown the resorting to show the original fragmentation match to get ideas about the substructure. We use the delta mass to tell what the neutral difference is between the two molecules, which appears to be chlorine. And essentially, I just want to go just look at that again, just to kind of set that in your mind about the importance of doing this. So I did a search. The delta mass table, when I was doing these 20,000 EI spectra, I created a neutral loss, a delta mass table. And I've got it on the internet. You can download it if you want. There's about 400 different ions or different delta masses that tell you something about the molecule. And then I have comments about, well, this is addition of a chlorine to an aromatic ring, et cetera. And the only thing I wish I had done that I didn't do, I didn't put the delta mass in accurate mass. I put it in nominal. And you can see here, there was some duplication in my table for 1, 2, 3, 4 things that could have lost 34 nominal. But if you look at the accurate mass, you'll see there's really only one possibility. It has to be this chlorine on the aromatic ring versus an aromatic ring with no chlorine. So it would be nice in the future if I could go back and do this and put them in accurate mass mode. And I've had some simple examples you can look at to see to get you an idea of what a delta mass is, like the difference between the delta mass between this phenyl ring with a phenyl ring with chlorine versus fluorine is a delta mass of 16. So that's just visually just to give you an idea of what I'm talking about. I always think it's interesting that the difference between a naphthalene ring and a benzene ring here is 128 and 78. So if you see a delta mass of 50, it just means that instead of having the phenyl ring, you'll have the corresponding naphthalene ring in your compound. Kind of handy again for extending your database from phenols, which are more common, to naphthals, which are less. So essentially what you have to do to put this together, I'll just reinforce what we talked about in the display. You can always resort by the ODOT product. Remember, the ODOT product is really the original match just based on the fragmentation pattern. If you just look at the fragments in the spectrum like you normally do, what would be the fit? And when you do that, it'll resort that with the highest number. And you'll find that the top 30 hits, when I was searching over in my whole database, the top 30 were all indicating that there are 2 chlorines on the ring, as opposed to being a chlorine on the ring over here. The delta mass only tells you that this differs by 34. So you could put a chlorine over here on this ring at this position here. But when you resort by the ODOT product, it tells you the substructure indicates the chlorines on the aromatic ring. It doesn't tell you exactly which place on the aromatic ring because the mass spec is not specific. You need something like NMR to tell you the exact position. And so essentially what you need to do to identify unknowns is to put this together. So you get the hybrid best results to tell you that, oh yes, one of the hydrogens on one of the rings has been replaced by chlorine, and then you resort by the ODOT product to see what the fragmentation looks like, and tells you that the substructure has to have this. And when you get through, you have a proposed structure that's consistent with fragmentation, but might or might not have been present in the database. So you can see how it extends the use of the database by these changes in the delta mass over spectra that are already in there that have similar relationships as far as it didn't change when you added this neutral molecule as far as how it fragments. And of course, you have all the accurate mass for all of these things also. So when you do the MS interpreter, if you wanted to look at this, you'll see that everything matches up accurate mass-wise for the proposed structure and substructures. So the last thing I want to talk about is this center display. Let's go back. The center display here, when you put it in the normal hybrid mode, is a little different. You have to get used to seeing what it's trying to tell you. And let's discuss that a little bit. In the bottom spectrum, the original ions in gray are shifted by the delta mass. What it's trying to do is line it up visually. So you can see originally the spectrum of the reference sample had an ion at 125, and to get it up to where it should be, delta mass was, it shifts it to this color. So it changes from the gray to a color. So if you're looking at the bottom one, it tells you that that's been shifted. Anything that's gray remains where it was, or I mean, not, no, I'm sorry, the grays have been shifted to the color, and the ones that remain in color here, like the 59.9898, they are fragments that were not shifted by delta mass to make them correspond to the top spectrum. So you're really looking at the fragment spectrum at the same time you're looking at the neutral loss spectrum. And on the top, it doesn't change anything. It's just trying to align the bottom to the top. So visually, when you do the overlay, you get used to it after a while. It takes a while, but about a day for me to get used to shifting, just ignoring the gray in my mind and looking at the gray shifted to color. But when I was first using it, sometimes I would go back and just right click in the center, do a neutral loss display, and I'll say, oh yes, I see why it matches. So that's pretty much what I wanted to show you. There's a lot of other things things to consider when interpreting hybrid searches for unknown identification. Determine the molecular formula using the isotope ratios in the original spectrum before you do the MSMS or import it. You want to get it down to one molecular formula. Sample history is always critical. You've got to assume that your identity is in relationship to what you know the sample history, the matrix was. Logical fragments using MS Interpreter. I use that a lot to send things over to confirm what I think might be a possible structure, and look at the other identified related compounds found in the sample. Just don't look at the one in the chromatogram that you're wanting to know what it is. See if you can identify other ones, and it all goes together to really just kind of confirm that your proposed structure is right by confirming related materials in the sample. And of course, talk to your customers. In my case, I work with organic chemists and engineers, sample submitters. Use their knowledge of organic chemistry to help you decide if your structure is reasonable. And of course, always use other techniques when possible, such as NMR, IR, etc., when they're available. So I hope this has been useful to at least get you up to speed in doing hybrid search. I am so excited about using hybrid searches in EI and just getting started myself in doing ones in MSMS, but I think the same types of useful information I found in EI hybrid searches will correspond to the type results I get in MSMS searches. So enjoy, and I hope you find this and the other webinars useful. So long.